Welcome to the Chapter 2, Part 2 lecture. You should use the information in this lecture to fill out your Chapter 2, Part 2 guided notes, which should be completed before you come to class. Now, in this part of the chapter, we're going to discuss how atoms work together to make bonds and to make molecules. First, let's define what a bond is. A bond is an interaction between two atoms. Typically, this involves the electrons in some way, and the atoms don't actually have to be hooked together, they can just be strongly attracted to one another. Whenever two atoms make a bond, they make something called a molecule. There are different kinds of combinations of atoms that exist. If molecules form that involve only one kind of atom, then we call that thing an element or an elemental molecule. A great example of this is O2, or oxygen gas that we breathe, because it's only made of oxygen atoms. Or a bar of pure gold would only be made of gold atoms. Compounds are molecules that contain different types of atoms. So for instance, water is a good example of a compound because it contains hydrogen and oxygen in combination. Table salt contains both sodium and chlorine. Now within a compound, the atoms are chemically bonded together, so they're not just hanging out together, they are attracted to one another for some reason, which we'll get into later. Mixtures are combinations of chemicals that are physically combined, but not chemically combined. So they're not bound together. A good example of this is sand and water. If you take a handful of sand and throw it in some water, they are going to be combined together, but they're not going to be chemically bound together forever. You could separate the sand from the water by filtering it, so by a physical means. Another fun example of a mixture is blood, and here's a nice slide of some blood over here. You can see all the cells. Blood consists of both solid parts, the cells, and liquid called plasma. And you can separate out these different elements using physical means. For instance, you can centrifuge blood and pull a lot of the cells out of it. So these are examples of mixtures. There are several different ways to represent molecules, and the most common is a molecular or chemical formula. In a molecular or a chemical formula, we use atomic symbols in combination with numbers, subscripts, and coefficients to represent the types of atoms involved in a molecule and the numbers of those atoms. So for instance, in H2O, the subscript 2 tells you that you have 2 hydrogen atoms involved and only 1 oxygen atom involved in that molecule, in that unit. Now, if you were to see it with a 2 in front of it, that's called a coefficient. And a coefficient tells you how many of these molecules you have. So if you just saw H2O by itself, that would tell you that you have 1 molecule of that in a jar, for instance. But if you saw 2 H2O, that would tell you that you have molecules in your jar. This diagram illustrates some of the other ways that we can represent molecules. First, we have that chemical formula again, like H2O. We also have something called a structural formula, which I will often refer to as a line model. And in a structural formula, the bonds between the atoms are shown with little sticks, little lines. And these are specifically covalent bonds, which we'll talk about in a little bit. There are also structural models. You'll see these a lot in your textbook, and these are three-dimensional models of a molecule. And finally, there are shell models. Shell models show the electron shells and the placement of the electrons on those shells. So you can see the interactions of the electrons between the different atoms involved. So we are going to play with both shell models, structural formulas, and we'll get into chemical formulas as well in this chapter. So why do atoms want to form molecules in the first place? Well, this has to do with the number of valence electrons that they have, and one of the biggest reasons is something we call the octet rule. The octet rule tells us that a happy atom will have a full valence shell. Now, if that atom can't completely fill that valence shell, if it can at least get 8 electrons in that valence shell, it's pretty happy. So for instance, if we have hydrogen, hydrogen has an atomic number of 1, which means it has one little electron on this first shell. Now that shell won't hold 8 electrons, but if it could add another electron to that shell, it would meet the octet rule and it would be happy. Other atoms are bigger. Carbon, for instance, has 6 electrons. Ooh, that's terrible. So it puts 2 in the first, and then it's going to put 4 more in the second shell. Terrible drawing. Okay, so how many can that second shell hold? Well, we could put 4 more in there to make 8. So a happy atom wants to either have a full valence shell, or if it can't totally fill it, 8 is the magic number. Atoms that do not meet the octet rule are reactive, and they want to interact with other atoms to fulfill the octet rule. So how do atoms go about fulfilling this octet rule? Well, there's several ways they can get electrons. They can steal electrons. If they have too many, they can give them away. Or they can share electrons with other atoms, and this helps balance them out and helps them meet that octet rule. Because of the octet rule, different atoms can make different numbers of bonds, and that's all dependent on the number of valence electrons that they have. So you need to be able to determine how many valence electrons an atom has. You did this in part 1 of the lecture by looking at the atomic number, counting out the number of electrons, and putting them on the proper shells. And I do want you to be able to do that for test 1. There is a second method though, and it involves the periodic table. If you look at the periodic table, you'll notice that these different columns have numbers. 1, 2, 3, 5, and then up here it goes to 13, 14, 15, 16, 17, 18, 19, 20. Okay, you can use these column numbers to tell you how many valence electrons these atoms have. So all of these guys in this first column here have 1 valence electron. All the ones in the second one have 2. Now to make this work, you need to skip this middle portion. Okay, so where it sinks down in the middle, skip that. And then the very next column you see is number 3. It's actually number 13. But those atoms will have 3 valence electrons, and so on. I'd like you to complete this your turn before you come to class. It's going to give you a little bit of practice with valence electrons. What you need to do is look up the atomic number for each of these elements, determine the number of valence electrons that each has, either by counting them up or by looking at a periodic table and looking at the column header. And then I want you to apply the octet rule to this situation. I want you to look at the valence shell and say, well, how many valence electrons are there? How many more does it need to meet the octet rule? If it has just 1 or 2 in the valence shell, then you can say, well, how many would it need to lose to meet the octet rule? Because they can ditch electrons too and make the next shell down their valence, and that fulfills the octet rule as well. So let me give you an example. The atomic number for carbon is 6. If you count that out, the number of valence electrons it has is 4. So to meet the octet rule, it could either gain or lose 4 electrons. Now in the case of carbon, it's going to gain 4 electrons. It wants to get 4 from somewhere, okay, rather than lose. Fill this chart out and bring it to class with you.